Good. So for double descent, there were two influential papers. The first one is what I drew on the blackboard, basically, and the second one here was from, well, many people, including Sutskever, then still with OpenAI, which he later left over a controversy. And the main experiment they showed is here. And so ResNet is, you know, by now one would say baseline model for image classification. And here is on a logarithmic scale for how many epochs it has been trained. And here is how wide a single layer is. So definitely going from left to right increases model capacity. And going over many epochs also will, if the model has enough capacity, will give you overfitting. And I hope you can see that there is a dark shade here and then a bit of a brighter shade there. Yeah? And so indeed, if you go here from left to right, or if you go from top to bottom, you see that the error is at first large, and then it decreases, and it comes up. That's the test error, and then it decreases. Okay, I got the colors wrong. So the error is high, the error becomes low, the error becomes high, and then it decreases again. Okay, they also made a second plot. It's just the information. So what we see now is here from left to right, each of the lines of the image are collected here in the plot that you see up there. So, and you see that for at least certain rows of the image, you have this clear pattern of the error coming down and then up and then down again. So this was observed in the field of neural networks. Okay, do you have a question there? Something you would like to share with our question? Anything? Okay. Good. Now, okay, deep neural networks do all kinds of things, but the maybe more surprising phenomenon is that you can demonstrate it even with linear models. And the figures here are taken from the draft of a nice new textbook by Petersen and Zech, who is in Heidelberg also. And let's start here in the top right corner. So we have some true underlying function. This is the dashed function f. And we have a couple of data points. They are noise free. Yeah, so there's no noise whatsoever. And here, these are a set of features. I believe these are random Fourier features. And so the, okay, these are called ansatz functions phi j. And so the estimate here is linear. One would simply take these, a combination of these functions phi j of x, and these functions are then multiplied with parameters beta j. So the functions themselves are nonlinear, but they are fixed. And the only parameters being learned here are the parameters, and the model is linear in these parameters. All right, now if only two of these random functions are used, well, we get, you know, this strange fit here. If 15 of these functions are used, pretty nice, fit is obtained. And if 18 functions are used, perfect interpolation is obtained. Yeah, so here using 15 of these basis functions, the fit we would call is pretty good, but it does not perfectly interpolate the observations. Yeah, so here, for example, you can see that the blue function is a little bit above the red point. Or here the blue function is a little bit below the red point. Or here it's maybe clearest, the blue function, our estimate, y hat, does not interpolate the data. Now, when these are 18 points, and when using 18 functions, yeah, so we have 18 measurements, we have 18 unknowns, we can solve here the linear system of equations. We obtain perfect interpolation and a horrible fit. Yeah? I mean, nobody would like to use this blue function here. So this is where the train error is good, but the test error would be very bad. This is at the interpolation threshold. And now comes the, so far everybody would be fine with it. And now comes the surprising bit that now if 40 functions are being used, so, you know, just 18 observations and 40 unknowns, we obtain a pretty nice fit. It's actually even a little bit better than the one we saw up there. Okay, and this is the phenomenon. This phenomenon is produced only if the least norm solution is found. So, of course, if we have 18 measurements and 40 unknowns, we have too many degrees of freedom. And so out of this family of solutions that have zero training error, we can pick the solution that has the smallest sum of squared coefficients. That's what's meant here. Yeah, so amongst all solutions with minimal risk, the one with the smallest norm of the parameter vector is chosen here. And only then do we observe this very nice fit here on the right-hand side. All right, and now we'll try and understand what's going on. Yes? So the question was, if we take the Fourier transform of these points and truncate, would we get similar behavior? Yes, this is true, because if we take, this is best the phenomenon that you are, okay, let's maybe take the simplest possible function. Yeah? Let's just take a signal which is all 0, and at one location we have a value of 1. And this is now in the spatial domain. And if we now expand this, we will find these Gibbs oscillations. It is not easy by combining Fourier functions to get a signal which is perfectly flat. So what you need to do is you need more and more samples in the spatial domain, or you need higher and higher k values or frequencies in the Fourier domain. and only when you use infinitely many sinusoidal basis functions can you reproduce a Dirac peak perfectly. Other questions, comments? Okay. So now for my argument, I need the notion of a Hough space. Who has encountered Hough space before? Or Hough transform? Computer vision again, yes. So let's consider a small regression problem. And we can look at it in the space of functions, or we can look at it in parameter space. And whenever we say Hough transform, we need to specify what family of functions are we considering. And here, here I will use just linear regression as or linear functions. And so our space has, our parameters are the slope and the intercept. I'm sorry if you cannot read this. Intercept. Okay, and if we now take a point like this one here, now there are many ways I can explain it. I could explain this point, for example, by a straight line going through the origin. So this would have an intercept of 0 and a slope of 1. Intercept of 0 and slope of 1 would be this point here. Or I could explain it by a linear regression which has 0 slope and an intercept of +1. It's this point here. Or I could explain it by anything in between, like this point. Or I can even explain it like so. This would be a slope of -1 and intercept of +2. Yeah? So basically what we find is that a point in the spatial domain will, in the space of linear regressions, correspond to a line in parameter domain. And if we now have a linear regression problem, so let's say this was my first observation, this is my second observation. For my second observation, I can construct a set of lines accordingly. So for example, this would be slope of 0 and intercept of 1. Slope 0, intercept 1, it goes through here. And or intercept of 0 and slope of 1/2, okay. So my blue observation would create this line here. Let's do a third point, and let's not make it fit perfectly. So I'm putting it a little bit above the others. I could explain it by a slope of 0 and intercept of maybe 1.25. Or I could explain it with a intercept of 0 and a slope that's a little bit lower than 1. All right, maybe like so. And it's not parallel to the blue one, so they will cross each other eventually here. Okay. Now, we were discussing the sum of squares function or if we talk about neural networks, we would call it the loss function. And this loss function would be the sum over all observations, the true label minus, and then we have our parameters, beta 1 minus beta 2 times x, and the whole thing squared. Now each of these lines here is one term in the summation, and each of these lines creates one of these parabolic valleys that we talked about so much last time. Yeah, so I'm sorry, your parabolic valleys are still here. So my first observation creates a parabolic valley which has a 0 along this line and grows parabolically away from it. So I could, if I wanted, draw the isocontours of this parabolic valley. And I can do the same for the second line here, another parabolic valley. And here I have another parabolic valley. And I'm adding all of them up. And so all together, okay, these parabolic valleys, they are all parabolae. And when I add up parabolae, well, I get a parabola. And in this particular case, this is a parabola which has, a pretty ugly shape because there's a strong correlation between what slope and what intercept I will estimate here. So in fact, I would say the true slope here is 0, and the true intercept is a little bit above 1. So my parabola will have its optimum here, but it will have this very degenerate shape here. This is the loss surface. So this loss is a function of my parameter vector. And this parabola here shows you how this sum of squared errors grows as we go away from the optimum. All right, and by the way, I don't want to use the time now. We'll do that in the exercise. If I move these points here further to the left, I would get a much better conditioned set of equations, because if I move it to the left, my estimate for the intercept is going to be much more stable. All right. So here with the Hough transform, I wanted to argue that each observation induces one line or a family of solutions with 0 error. Okay, so I've written here, each single observation induces one set of solutions in parameter space. And here, unfortunately, I have 3 observations, and the 3 sets of solutions that they induce are not compatible. So if now this picture was faithful, yeah, it was accurate. I will now make it less accurate, but a little bit simpler, yeah, just for visual clarity. So what we had here, let's say those were 3 points. So if I have 3 points here, I obtain 3 sets of solutions. And these 3 sets of solutions here do not coincide in a single point. Yeah, and this is why we call this problem here, if we now talk linear, okay, this is what I'm talking here is only the Hough transform of linear models. So if I have 3 observations and if I only fit linear models, here I have an overdetermined system of equations. Or from the machine learning point of view, I can say this is an underfit because I have 3 observations and only, 1 straight line, so I cannot fit them perfectly. Now, if I have only 2 points, then I will have here, 2 models, and I have a unique solution with 0 mistake. And this problem was overdetermined. This problem here, I can simply say it's determined, or I can say the linear system of equations has a perfect solution, or I could say this is fit. Okay? Through 2 points, I can always fit a straight line perfectly. And now I can go 1 step further and say, okay, I have 2 points. Maybe I have this point here and this point there. But up here, the model that I was using was y equals y hat of x was beta 1 plus beta 2 times x. And now I'm using another basis function. I'm saying y hat of x was beta 1 plus beta 2 times x. And I'm introducing a new basis function, b3 times the square root of x. So my new basis function would be the square root of x. And here, I had these parameters beta 1 and beta 2. Now I have 3 sets of parameters. I have beta 1 and beta 2. I'm trying to copy this faithfully, more or less. But I also have this new axis now. I have a new axis beta 3. And now my my first line here in 3D space, this becomes a plane. Okay, let's say this is a solution. This is where they intersect. And I'm now trying to indicate that we now have a plane in this new dimension. And now it gets challenging with my graphics capabilities here. Okay, I hope ideally you're able to see here a green surface and a blue surface, and they are intersecting each other along this red line. Okay, one person sees it. Thank you. Thank you so much. You're making my day. All right. I have a prettier picture on my computer. So okay, on the blackboard, I drew the example where we have 2 lines, and if we open a new dimension, we have 2 surfaces. Here I'm showing you a different picture. in this 2D space, I have 3 lines. And if we go to 3D space, we get these surfaces. Okay, let's try and flip back and forth. You can see what I mean. So this would be my 2D parameter space. And here is my 3D parameter space. In 2 dimensions, each point engenders a line. In 3 dimensions, accordingly, each point engenders a surface. And here I have had 3 observations corresponding to 3 lines. And if I add another feature to my feature space, then they become surfaces. And in this particular case, well, the surfaces intersect somewhere. Yeah, so for 3 points, 3 unknowns, I can find a perfect fit. I can find a perfect solution. All right, but now I want to return to my uglier picture on the blackboard. Because some of you can see a green surface and a blue surface, and the 2 are intersecting along a red line. And this red line is the set of solutions which are compatible with these 2 points. And they're all perfect solutions. They have no, they are all perfect fits to the data. I can also call this a solution space. And for this particular model here, I can show you some points from the solution space. So for example, a straight line fit is a perfect solution, right? But I can also say, look, I'm going to use a solution which only uses my 3rd feature, square root of x, and doesn't use the other 2. And it's also a perfect fit. And now you can imagine that as I change my parameters, in between, I have a whole family of solutions that are all perfect fits to my 2 observations. And this family of solutions, these are points here along this solution space. Now, which of these solutions should we prefer, if any? You know, they're all solutions. They all fit the data perfectly. Yes? The suggestion is, let's use the solution that needs the fewest parameters. And well, the solution that uses the fewest parameters, of course, would be this one here. I explain it only in terms of the new feature. I forget the other one. That would be a plausible approach to choose the solution with the fewest parameters. But solution with fewest parameters would be a solution only if this red line segment, if it intersects one of the coordinate axes perfectly. Now, the way I constructed it, that's the case. Yeah? So square root of x is enough. But if I shift my points up a little bit, let's say my new observations are these, then I can no longer just use the square root of x to fit them perfectly. I need square root plus a bit of intercept. So I'm trying to replicate this picture here. Let's say we have beta 3, beta 2, beta 1, and our original solution in the space of betas was, let's say, somewhere here. And now I have this set of possible solutions. And now let's pretend that that my line segment does not intersect, it does not go through one of the coordinate axes. Do you have another suggestion for what could be the best solution? Yes? Yeah, that's quite plausible, right? Let's pick the solution which is closest to the origin in parameter space. You know, I mean, all our solutions, we have to pick one somehow. Yeah? And we might as well say, all right, let's pick the one which is closest to the origin. And let's go back to the pretty pictures here from linear regression. If you look again at this formula here, that's exactly what it does, yeah? Amongst all solutions, it picks the one which has the least norm, yeah? If you forget about the subscripts, there's an arc min W. Yeah, you pick amongst all perfect fits, you pick the perfect fit which has the smallest norm. And this perfect fit, which has the smallest norm, is the one that was shown here. And all the other perfect fits, well, they could look as bad as this or even much worse, right? We can have solutions, let's say, okay, plotted here is what's the norm of the solution vector. And here the smallest solution vector that we can find has, I don't know, 0.05 or something. But I could create a solution vector which has a norm of 1,000. Yeah? This would be, you know, like the oscillatory picture, but with huge oscillations. It's a perfect fit, but somehow a terrible explanation of the data. So what this experiment here argues is that picking a solution with a small parameter vector, if we have infinitely many solutions available, is maybe a decent strategy. And what you saw on the blackboard is just a translation into, let's say, the space of into the space of linear algebra, or into the space of having overdetermined, determined, or underdetermined systems of equations. This here is an underdetermined system of equations. Or I could say this is an overfit. So we had these three cases here: overdetermined, determined, and underdetermined. And in the underdetermined case, we have to make a choice somehow. And the argument here goes, all right, maybe it's reasonable to pick the solution with the smallest norm. Okay. Let's talk about, and now is a question for you. Let's talk about which solution will be found if I initialize the problem either with 0 or with a normal distribution around 0, and if I use gradient descent. So remember that this here was a picture of a parabolic valley. So here I can draw the equicontour lines. This was a parabolic valley which had its minimum along the green line. This was another parabolic valley which had its minimum along the blue line, parabolic valley. Here I have these parabolic planes. Yeah? The loss is 0 along the plane, and it grows parabolically as we go away from it. Same for the green plane. So the sum of parabola is a parabola. And I have two questions for you. The first question is, if we now want to fit this kind of model using gradient descent or stochastic gradient descent, and we start at the origin, where will we end up? And my second question is, if we don't initialize at the origin, but if we initialize according to a normal distribution, which is around the origin, and that's what we do with neural networks, right? With neural networks, we use a Keiming initialization or a Hay initialization, which means we pick random values for our initial parameters, and we adjust the variance a little bit, but basically we use a normal distribution for initialization. Please talk with your neighbors and figure out, what's the distribution of outcomes that we get if we use gradient descent, either starting from 0 or from a normal distribution around 0. Up to you. Please use a few minutes to discuss it. Not too many, because you want to go home. You're in video here, yeah? If you come to the front. So maybe we'll talk later, okay? Okay. Let's see what you have found. I tried to make a bigger and prettier picture. So again, the red line segment is the solution space. All of these solutions are perfect fits to our data. And I tried to indicate, so we have a parabolic set of planes here and another parabolic set of planes. We add them up, and what I get is I've called this a parabolic cylinder. So my error is 0 along this red line. It grows quadratically as I go away from the line. And the question was, if I start gradient descent at the origin, where will I end up? Yes? Yeah, perfect answer. Yeah, so if I start gradient descent here, and for the arguments that you have given, I'm always orthogonal to the isocontour or surfaces, and I will go to the closest point on, that's the right angle. I will go to the closest point. I will find the least norm solution. Perfect. Second question, what if we initialize with a normal distribution around the origin? What distribution of solutions will I get? Yeah. Yeah. So if I project a normal distribution onto a plane, if I project a 3D normal distribution onto a 2D plane, I get a 2D normal distribution. If I project a 3D normal distribution onto a line segment, in the sense of gradient descent, I will get, like you said, a normal distribution which is centered around this closest point. So I'm sketching it now as a 1D thing here. This, if I initialize with this family of solutions, I will end up with that family of models. Good. And so this is now working our way towards neural networks, because neural networks, as you know, are optimized with gradient descent. And so maybe what happens in these over-parameterized networks is that if we use this type of Keiming or Hay initialization, maybe we find solutions which have smallest norm, even without explicit, weight decay or regularization or anything of that kind. Okay, so this is one aspect of how you can start and explain this amazing phenomenon, which hasn't really made it to the textbook yet, of double descent. Thank you very much. See you soon.